step cafe. We have to make everything science, technology, engineering, and mathematics easy to learn, fun, interesting, and easy to recall. Now, I want us to do some exercises on rotational dynamics. We can also call it circular motion analysis. Most people are familiar with circular motion on particles, but you can see from our lectures, we have extended it to rigid bodies. So in case you have any itch, you can refer to the main lecture. Now let's start and treat some examples. Please, before we go on, I'd appreciate if you can assist by sharing, comments, subscribing if you haven't, and any other help you can render to encourage. Thank you very much. Let's handle the first example now. An object of mass 4 kg moves around a circle of radius 6 meters with a constant speed of 12 meters per second. Calculate 1, the angular velocity, 2, the force towards the center. We have said that for circular motion, V equals omega r. And our V in this instance is 12 meters per second. Our radius is equal to 6. So omega will be V over r, which is 12 over 6. That is 2 rads per second. And we also asked the force towards the center. We also show that force towards the center is equal to mv squared over r, which is also equal to mw squared r. So in this instance, our n is equal to 4 kg. Our omega is 2 rad per second, and our radius is equal to 6. So force towards the center, F, is equal to 4 times 2 squared times 6, and that is 96 Newton. So that is the force towards the center. Very simple. An object of mass 10 kg is swirled around a horizontal circle of radius 4 meters by a revolving string inclined to the vertical. If the uniform speed of the object is 5 meters per second, calculate 1, the tension in the string, 2, the angle of inclination of the string to the vertical. Now, you have the situation. We have a string inclined to the vertical like this, and it's moving around. So here, we have the string, we have the weight, and we have the centripetal force, mv squared over r. This tension here will handle this one and mg. So we have T here. So if you look at it, we have theta here. So we have it like this. So the mv squared over r will be this, or mw squared r, mg, and we have T. So they are also asking for this theta here, because it will be equal to this one. Can you see now? So, and now, if you draw this triangle, you will see that T, because this one and this one are perpendicular. So mg here, mv squared over r and T here. So you can see the sum of these two will give this using Pythagoras theorem. Let's find what weight is and centripetal force. So mg, weight, which will be, what is the mass? 10 kg. M equals 10 kg. And let our g be 10 meters per second squared. So we have this one to be 100 Newton. Let's see what our centripetal force is. We are told that, and the velocity is 5. 4 times 5 squared. And what is the r? And radius is also 4. So this one is giving us 25 Newton. Therefore, the centripetal force will be equal to mv squared over r. What's our n? 10. What's our v? 5. And what is our r? Radius is 4. And that is going to give us 62.5 Newton. Therefore, T will be equal to 100 squared plus 62.5 squared. And that gives us 117.92. So the value of the tension in the spring is 117.92 newtons. We are also asked the angle between. So if you look at this, tan theta is equal to mv squared over r divided by mg, which is equal to mv squared over r times 1 over mg. So if you cut this, you will see that tan theta is equal to v squared over rg. We have established this one also before. So let's find what tan theta will be. So tan theta will be equal to 5 squared over 4 times 10, which is 25 over 40. Therefore, theta will be equal to half tan 25 over 40, which is equal to, let's find that, 32 degrees. So the angle of inclination of the string to the vertical is 32 degrees. Now let's undo this. A racing car of 1,000 kg moves around this bank track at a constant speed of 108 km per hour. Assuming the total reaction at the wheels is normal to the track and the horizontal radius of the track is 100 meters. Calculate the angle of inclination of the track to the horizontal and the reaction at the wheels. Now we have a situation like this. So we have a situation like this, and we have the car like this. Now, so we are told that we should take the reaction as normal. That is, the total reaction is perpendicular like this. And the radius here, we are told is 100 meters. And the weight of the car, we are told is 1000 g. That is 1000 times acceleration due to gravity. We also have, so we have r like this. We have mv squared over r provided by the car, by the reaction components of the car towards this place. So this is what we have now. We have the weight down, we have the reaction like this. So let's draw the component like this. And we have theta here. So we have the car like this. If you look at it, this one is theta to the horizontal, and the reaction here will be perpendicular. So from here to here is perpendicular. So by the time you look at it, this place will be theta. So from here to here too will be perpendicular. This place will be 90 minus theta. So from here to here now will now be theta, because 90 minus theta plus theta will give you 90 degrees. So that's what we have here. So we have this one already resolved. Now, this place is mv squared over r. And this place, we have mg. That is, so this is f and this is w. So we have it like this. This is r. That is r1 plus r2 equals to r2. This component will supply us this mv squared over r. And we have the mg down here. We are asked two questions. Assuming the total, okay. Calculate the angle of inclination and the reaction at the wheels. So with this, we have something like this. Mg, and we have the reaction like this. So we have mg here, the w, f, mv squared over r here, and we have the rt here. So this angle here is this one. So which is equal to this one. You can see. So that is our theta that we are looking for. Now, if I want to find theta, I can say tan theta is equal to mv squared over r divided by mg, which will be equal to mv squared over mrg. V squared over rg. So from here, I know my value for v. Let me find my v, my r, and g. So g is 10 meters per second square. R, we are given r to be 100 meters. And v, we are told it is 108 kilometers per hour. So you know we have to convert to meters per second. And the procedure is 108 times 10 over 36. And by the time you cancel, that's going to give you 3. So we have 30 meters per second. So from there, let me find tan theta. So tan theta now will be equal to 30 squared over 100 times 10, and that is 900 over 1000, 0.9. 0.9. So theta, the angle, is equal to 41.99, approximately 41.99 degrees. So approximately 42 degrees. So that's approximately 42 degrees. Now, since I know what mv squared over r, I can get it. I can get what mg is. I can easily use that one to find out if I don't want to use angle. So let's see. So RT, reaction at the wheels, will be equal to square root mg squared plus f squared, and that is, this is equal to 1000 times 10 squared plus 1000 times 30 squared over 100 all squared at the same time. So I can bring out, well, let me just do it straight. That will be, so that gives me 13,454 newton. So that's what I got as the tension. As the tension in the, no, that is what I got as the reaction at the wheels. That's the reaction at the wheels. Sorry. An object of mass 8 kg is whirled round a vertical circle of radius 2 meters with a constant speed of 6 meters per second. Calculate the maximum and minimum tension in the string. This is how we go about it. We have an object describing like this. So at different times, it is like this. The maximum tension in the string is there. And you discover it is mv squared over r plus mg. And in this place, the minimum tension here is going to be mv squared over r minus mg. So let's calculate what T1 is. Our quantities, mass is 8 kg. V, velocity is 6 meters per second. G is 10 meters per second squared. And then R, radius, is 2 meters. Therefore, maximum tension will be equal to N into 6 squared. What's N? 8 into 6 squared divided by 2 plus 10. And by the time you look at it, it's going to be 8 times 20. Because this one here is 18. And that is going to give us 224 Newton. And minimum tension is equal to 8 into 18 minus 10, which is 8 times 8, which is 64 Newton. So that's a simple calculation there. Another question. Calculate the force necessary to keep a mass of 0.2 kg moving in a horizontal circle of radius 0.5 meters with a period of 0.5 seconds. Number 2. Calculate the mean angular velocity of the Earth, assuming it takes 24 hours to rotate about its axis. 3. An object of mass 2 kg is 1 at the poles, 2 at the equator. Assuming the Earth is perfect sphere of radius 6.4 times 10 to the power 6 meters. Calculate the change in weight of the mass when taken from the poles to the equator. Now, we have the simple situation of this. Let's try this first one. It says that we should calculate the force to keep a mass. And we know that in this situation, the centripetal force is the force we use to keep it, and it's towards the center. It's going to be mv squared over r, which is also equal to mw squared r. So our mass here is 0.2 kg. And we are told that our R is 0.5 meters. So period is 0.5 seconds. Please, I want us to understand what this period means. Period is the time that you take to move round the circle once. That is the period. So we have period. So P is 2 pi over W. I want you to understand it. Time for one revolution. Time for one revolution. So you can now say that W is equal to 2 pi over P, which is 2 pi over 0.5. That is 4 pi. Therefore, our F now, we can calculate it to be 0.2 times 4 pi squared times 0.5. 0.2, this is the mass. I'm using this formula. Times 4 pi squared times 0.5, because this is our omega. And let's calculate what that will give us. And that's giving us 15.79 Newton. The second question says, calculate the mean angular velocity of the Earth, assuming 24 hours to rotate about its axis. We know that for full rotation, 1 revolution, or full rotation is equal to 2 pi rad. And time, or period, then it's a period. That is time for one full rotation is equal to 24 hours, which is 24 times 60 times 60. This is 60 minutes, 60 seconds. And that is giving us 86,400 seconds. 86,400 seconds. So, W, that is angular velocity, mean, will be equal to 2 pi over 86,400 rad per second. And that is 7.2722 times 10 raised to the power minus 5 rad per second. The last part is now asking us, an object of mass 2 kg is at the poles, 2 at the equator. Assuming the Earth is a perfect sphere of radius 6.4. Calculate the change in weight of the mass when taken from poles to the equator. This is the shape of the Earth. This is the pole, north and south. At the north and south pole, weight will be equal to mg. And here too, weight will be equal to mg. Why? The rotation along the side is not affecting the weight. Now, when taken to the equator, the new weight, because this one here will be trying to reduce the weight. It will be reducing the weight. Let me do something like this. Assuming it is on the spring balance. So, the weight here normally is supposed to be mg. But due to the rotation of the Earth, it will affect the weight. It will reduce it by nw squared r. You understand? Because of this rotation here, it will be like it is pushing this weight out. Try to rotate anything. It will be like the weight wants to eject from the string. So this is what the new weight will be. And we are asked the change in weight. So change in weight is actually nw squared r. And we have gotten our w here. We know our n, we have been given 2. So it will be equal to 2 times 2 pi over 24 times 60 squared, all squared, times 6.4 times 10 raised to the power 6. And let's see what this one will give us now. So, the change in weight will be mw squared r, and that is 0.0677 newton. Very straightforward. A stone is rotated steadily in a horizontal circle with a period t by a string of length L. If the tension in the string is constant and L increases by 1%, find the percentage change in T. Now let's get our quantities. We are told that the initial period is T, which is 2 pi over W, and the length is L. Length is L. We are also told if the tension in the string is constant, that is, let's call tension to be equal to F. If the tension is constant and L is increased by 1%, find the percentage change in T, that is, change in T. Let's look at the relationship between F, L, and T. We can see that T, omega is equal to T over 2 pi over T, that is angular velocity. Angular velocity. Then we can now say the relationship between them, F will be equal to, since the mass is constant, F will be m w squared L. We also told that F is constant in this situation. So we can now say, so what is changing now? L is changing. At the same time, this one will change. So once this one changes, it will affect change, it's because change in C. Now, we can now say F will be equal to m times 2 pi over T into L. At the same time, we can now say the new period will be equal to T1. Therefore, F is also equal to m into 2 pi over T1 all squared times new L. And we are told new L. L1 is equal to L into 101 over 100. It is increased by 1%. So, to L1, which is n into 2 pi over T1 all squared times 101 over 100 L. Now, we want to find the relationship between T1 and T. That is what we are after. But we know that the tension here is equal to the tension here. Therefore, n into 2 pi over T all squared into L is equal to n into 2 pi over T1 into 101 over 100 L. Therefore, I can cancel this. I can cut this. Now, let me now see. Okay, this one is squared, please. I can cancel this one also. Therefore, 1 over T all squared is equal to 101 over 100 times 1 over T1 all squared. Find the percentage change. So, once we have gotten into this stage, we can also say the reciprocal is true. That is T squared is equal to 100 over 101 T1 squared. So we can extend by saying that T1 squared will be equal to 101 over 100 T squared. So invariably, you can now say T1 is equal to T into root of 101 over 100. So change in T is equal to T1 minus T. Okay, let me do it straight. Percentage change in T. Percentage change in T is equal to T1 minus T over T times 100. Let's see what that one will be. So, you have discovered that percentage change in T will be equal to, what is T1? T into root of 101 over 100 minus T over T times 100. And if you look at it, T is common here. So it's going to give us root of 101 over 100 minus 1 times 100. And so that's what that one gives us. 0.4988%. So change in T is 0.4988%. A mass of 0.2 kg is swirled in a horizontal circle of radius 0.5 meters by a spring inclined at 30 degrees to the vertical. Calculate the tension in the spring. 2. The speed of the mass m in the horizontal circle. B. An object of mass 0.5 kg is rotated in a horizontal circle by a string 1 meter long. The maximum tension in the string before it breaks is 50 Newton. What is the greatest revolution per second of the object? So the first one says a mass. So let's get it. M equals 0.2 kg and it's swirled in a horizontal circle of radius r is 0.5 meters by a spring inclined at 30 degrees to the vertical. Calculate tension in the spring. B, the speed. So we have something like this. And we are told that this is 30 degrees. So we can see that this is T. This one will give us the mv squared over r. And this one will give us mg. So going by this, we can draw the diagram like this. mv squared over r, mg. And since this is 30, this place 2 will be 30 degrees. And this is T. So T, from what you have seen there, T will be equal to, T cos 30. So if you look at it, T cos 30 is equal to mg. Therefore, T will be equal to mg over cos 30 degrees. And that is 0.2 times 10. If g is taken as 10 meters per second square, cos 30 degrees. And that's going to give us 2.31 Newton. We also asked the speed of the mass m in the horizontal circle. That is, you can see that that one will correspond to T sine 30. Therefore, T sine 30 will be equal to mv squared over r. Or let's go with tangents. Let's go with tangents. I rather now. So we have mv squared over r divided by mg is equal to tan 30. So what's our r? Our r is equal to 0.5. Therefore, we can now say v squared over rg is equal to tan 30 degrees. So we are looking for v squared. So v squared will be equal to 0.5 times 10 times 30 degrees. And that gives us 2.887. So v, the velocity, that's what you are asked to find now. It's going to be root of this. It's root of 2.887. And that is 1.7 meters per second. So the velocity by which it rotates is 1.7 meters per second. The next one is this. The next one also says an object of mass 0.5 kg is rotated in a horizontal circle by a string 1 meter long. The maximum tension in the string before it breaks is 50 Newton. Now, we can also get that one with ease. So, we have 50 Newton will be equal to n v maximum squared over r. Or let's make it like this: n w squared maximum times r. Because with this I can easily get the number of revolution per second after getting w. So w m squared will be equal to 50. What is our m in this instance? 0.5. R is equal to 1 meter. So it's going to be 0.5 times 1, which is 100. So maximum angular speed is equal to root of 100, which is 10 rads per second. We are now asked the number of revolution per second, the maximum revolution per second. So that is going to be the frequency, and frequency is equal to 1 over t, which is equal to w over 2 pi, and that is 10 over 2 pi, 5 over pi. Let's see what the answer is. 1.59 revolution per second. 1.59 to revolution per second. So that is the maximum revolution per second. A mass of 0.4 kilogram is rotated by a string at a constant speed v in a vertical circle of radius 1 meter. If the maximum tension of the string is 3 Newton, calculate 1 v. 2. The maximum tension. 3. The tension when the string is just horizontal. Second part. What force is necessary to keep a mass of 0.8 kg revolving in a horizontal circle of radius 0.7 meter with a period of 0.5 seconds? Pi equals 10. Pi square equals 10. Let's do the first part. We have a mass being rotated in vertical circle. The minimum tension is here, and that is mv squared over r minus mg. The maximum tension is here, and that is mv squared over r plus mg. And the horizontal here, c here, will be equal to t horizontal will be equal to mv squared over r. And we are told that the minimum tension is 3. Therefore, 3 equals to mv squared over r minus mg. Now let's extract our figures. M equals 0.4 kg. G is 10 meters per second square. And then R is equal to 1 meter. Let's find our V. Okay, what are we asked to find first? V. So 3 equals to 0.4, you can say. It's common to both. V squared over 1 minus 10. So I can have 3 over 0.4 plus 10 equals to V squared. So what is V squared now? So V will be equal to, this one is 17.5, square root of 7.5, and that is 4.18 meters per second. Now the next part says the maximum tension. So T max, let's do something. T max minus T min will be equal to mv squared over r plus mg minus mv squared over r minus mg. So what is the difference now? It's going to be 2mg. Therefore, T max will be equal to T minimum plus 2mg, which is 3 plus 2 into 0.4 times 10, and that is 11 Newton. So that's our T max. That's our T max. Now we also ask, what is the tension when the string is just horizontal? When the string is just horizontal, I call it TH minus T minimum will be equal to mv squared over r minus mv squared over r minus mg. So you can see that this one equals to mg. Therefore, T horizontal will be equal to mg plus T minimum, which is 0.4 times 10 plus 3, and that is 7 Newton. Very easy to get. Now we are asked, what force is necessary to keep? So we have mass m equals 0.8 kg, and radius is equal to 0.7 meters. We are given period t is equal to 0.5, which is equal to 2 pi over w. So our w, our omega, sorry, is equal to 2 pi over 0.5, which is 4 pi. Now, the force necessary to keep it revolving, that is F, will be equal to m w squared r, m omega squared r, and that is 0.8 times 4 pi all squared times 0.7, and that gives you 0.8 times 0.7 times 16 times pi all squared. And we are told that pi square should be taken as 10. So we can now say 0.8 times 0.7 times 16 times 10. That is F. So which will be equal to and that is 89.6 Newton. 89.6 Newton. So that's the force necessary to keep it revolving. Now, 1. A spaceman in training is rotated in a seat at the end of a horizontal rotating arm of length 5 meters. It can withstand acceleration up to 9g, that is 9 times acceleration due to gravity. What is the maximum number of revolutions per second permissible? G equals 10 meters per second squared. 2. A small body of mass m is attached to one end of a light inelastic string of length L. The other end of the string is fixed. The string is held taut and horizontal, and the body is then released. Find the values of the following when the string reaches the vertical position. A. The kinetic energy of the body. B. The velocity of the body. C. Acceleration of the body. And D. The tension in the string. The tension in the string. Now the first one is like this, and it's being rotated. And we are told that the length of the arm is 5 meters, which means that it can withstand acceleration up to 9g. That is A max will be equal to 9g, which is 9 times 10, 90 meters per second squared. That's what the spaceman will withstand. And we know that A is equal to v squared over r, or w squared r. So we know our r is 5 meters. Therefore, 90 will be equal to w squared times 5. So w squared will be equal to 18. Therefore, w will be equal to 3 root 2 rad per second. Now we are asked maximum number of revolution per second. To find number of revolution per second, that is going to be w over 2 pi revolution per second, and that's going to be 3 root 2 over 2 pi. So let's see what that gives. That is 0.6752 revolution per second. Now for the second part, we are given an impression like this. Let's say this is the weight, and this is the length. This is the string. We are told that the length is L. The string is L taut at the horizontal, and then released. Find the values for the following. Well, so the string is now allowed to fall until it gets to the vertical like this. So we are now asked the kinetic energy at this point. Okay? The potential energy at this point relative to this tree will be NGL. So when it gets here, all the potential energy will be converted to the kinetic energy here. So KE, kinetic energy at vertical position, will be equal to NGL. That's it. We are now asked the second part, the velocity of the body. The velocity at this point. So for the velocity, we know that this one, mgl, will be equal to half mv squared. So to find v now, let's call this. V squared will be equal to 2gl. Therefore, v will be equal to root of 2gl. That is the velocity at that point. Now, we are asked the acceleration. The acceleration is a over r. C, a equals to v squared over r, and r equals to L in this instance. Therefore, acceleration, and that is only to the center, is going to be 2gl over L, which is 2g. That is the acceleration. Acceleration here is 2g. The tension in the spring for the D part, T is equal to mg plus mv squared over r. And from this D part, we have realized that A towards the center is 2g, and that is v squared over r is equal to 2g. Therefore, tension is equal to mg plus 2mg, which is 3mg. That is it. So the tension is T here is equal to mg plus 2mg, 3mg. A stone of mass 500 grams is attached to a string of length 50 centimeters, which will break if the tension in it exceeds 20 Newton. The stone is whirled in a vertical circle, the axis of rotation being at a height of 100 centimeters above the ground. The angular speed is very slowly increased until the spring breaks. In what position is this break likely to occur, and at what angular speed? Where will the stone hit the ground? Now for the question, we have this as the situation. It says the length of the cord 50 cm, which we call 0.5 meters. At the end is attached a mass of 500 grams, which is equal to 0.5 kilograms. Please, we convert everything to SI units. Then it is now well, and the maximum tension that should be there is 20 Newton. We are told the mass is 0.5, looking for any other thing. Then we are told, we are asked, in what position is this break likely to occur? Because this is the position I think the break is likely to occur. Because T at this point is equal to mg plus mv squared over r. That is one. It now asks, at what angular speed? Let us find the angular speed now. We are going to have it like this. This one is also equal, you can also make it like this, mg plus n omega squared r. Therefore, 20, that is T max, that is the maximum force, is equal to mg plus n omega squared r. And we know what our n is, 0.5. Therefore, we can say 0.5 into g plus omega squared r plus omega squared r. Therefore, 40, we know our g to be 10 plus 0.5 omega squared, because r is 0.5. Therefore, we can also say that 40 minus 10 is equal to 0.5 omega squared. So 30 over 0.5 is equal to omega squared. So omega will be equal to square root of 60. And that is square root of 60, which is equal to 7.746 rad per second. So that is the angular speed at which it is likely to occur. And we are asked, at what position will it hit the ground? Now, if you notice, you are told that the axis of rotation is 100 meters above, 100 centimeters. The axis of rotation is 100 centimeters above the ground. That is, if this is the ground level, from this place to this place is 100 centimeters, which is 1 meter. We know what our omega is at this point, root 60. And our velocity at this point, v, will be equal to 0.5 root 60. From our knowledge about motion under gravity, we know that the velocity here is tangential, and this is 0.5 root 60. And the time will be dependent on the remaining distance here. The distance from here to here is equal to 1 meter minus 0.5 meter, which is 0.5 meters. So let's use that one to calculate our t. Let's use that one to calculate our t. 0.5 equals ut, that is u vertical t plus half at squared. Initial velocity is 0, so we have 0.5 equals to have, what is our A? G. So from here, our t squared, we get it. So we have this one to be 1 over 10 equals to t squared. So t equals to root of 1 over 10. That is t. And along the horizontal, the velocity is constant. So the point at which it will hit the ground, the point at which the mass will hit the ground is equal to 0.5, that is the radius, times omega root 60 times time root of 1 over 10, and that is 0.5 root 60 over 10, 0.5 root 6 meters. So let's see what that one will give us. That will be 1.225 meters away from this point. 1.22 meters away from this point. And if you calculate it from this point too, you just subtract 0.5 meters. So you are able to get this one to be 1.225 meters. Or if we convert it to centimeters, it will be 122.5 centimeters. Very simple and straightforward. A special prototype model aeroplane of mass 400 grams has a control wire 8 meters long attached to its side, to its body. The other end of the control line is attached to a fixed point. When the aeroplane flies with its wing horizontal, in a horizontal circle, making 1 revolution every 4 seconds, the control wire is elevated 30 degrees to the horizontal. It's elevated 30 degrees to the horizontal. Draw a diagram showing the forces exerted on the plane and determine A, the tension in the control wire, B, lift on the plane. So we have a situation like this. And this represents the plane. Let me draw this way. So it is now moving around at the top like this. And the radius from what we have here is, okay, the length of this wire is given as 8 meters. That's the length of the wire. I was told that when it is moving, it is 30 degrees to the horizontal. That is the inclination to the horizontal. Then it will move round and making 1 revolution every 4 seconds. So which means that it travels 2 pi rad every 4 seconds. Therefore, angular velocity will be 2 pi over 4 rad per second, which is 0.5 pi per second. So that is the angular velocity. And as it is moving like this, there is a lift, there is mg down, there is t here, and there is mv squared over r supported by the string, by the wire here, the portion of this one. So let me draw it. So this t will give us this portion, the component of t along the radius. So we are going to have something like this. So you have this t, you have this mg, you have this lift, and you have this mv squared over r, and you have this as 30 degrees. We have the tension in the wire, the tension in the control wire. As you can see, along the vertical, that is t sine 30 will be equal to L minus mg, and t cos 30 is equal to n v squared over r, or n omega squared r. Now, the r we are talking about is the r here. R here. Now, let's bring out our figures. R is equal to 8 cos 30. This is it. So this place is also 30 degrees. So this place R is equal to 8 cos 30 degrees. our N is 400 grams, which is 0.4 kg. And we have gotten our omega. We have gotten it. Therefore, C is equal to N omega squared cos theta. And that is going to be 0.4 times 0.5 pi all squared times 8 cos 30 degrees over cos 30 degrees. So we have this, cancel this. Therefore, maybe I should rub this off. So C, from here, C will be equal to 3.2 into 0.5 square times pi square. This one and this one is 3.2. 0.5, this one is cancelled. So we are going to have, and we have been told that this one is 10. So we are going to have 32 times 0.25, which is 8 Newton. So our T is 8 Newton. That's our T. Now let us find the lift. From what we have done here, L is the lift. And how do we find L? L, see please, L will be equal to T sine 30 plus mg. That is the lift. So which is equal to 8 sine 30 plus 0.4 times 10. And this sine 30 is 4. So 0.4, that is 4 plus 4. And it's equal to 8 Newton. So the lift is 8 Newton. The tension is also 8 Newton. A disc of moment of inertia 10 kg/m square about the center rotates steadily about the center with an angular velocity of 20 radians per second. Calculate its rotational energy. 2. Its angular momentum about the center. 3. The number of revolutions per second of the disc. Here we have I to be equal to 10 kg/m square. Omega 20 radians per second. Now we are to calculate one rotational energy. Rotational energy. And that is going to be half I omega squared. This is half times 10 times 20 squared. That's 400, 200, that's 2000 joules or 2 kilojoules. The second one is its angular momentum about the center. That is angular momentum. It will be equal to I omega, which is 10 times 20, which is 200 kilogram meter squared per second. The third one, number of revolutions per second of the disc, and that is number of revolutions per second. That will be 20 over 2 pi. Let's see. And that will be equal to 3.183 revolution per second. A constant torque of 200 Nm turns the wheel about the center. The moment of inertia about this axis is 100 kg/m squared. Find 1. The angular velocity gained in 4 seconds. 2. Kinetic energy gained after 20 revolutions. Now, there are some expressions already known with respect to torque, angular velocity, angular acceleration. We know that torque is equal to moment of inertia times angular acceleration. And we are told that the torque about the axis is 100 kg/m squared. Initial angular velocity is 0. We are asked to find the angular velocity gained after time t 4 seconds. Now, and we are told that the torque is 200 Newton meter. Therefore, from here, you know that 200 Newton meter is equal to 100 times alpha. So Alpha is 200 over 100, which is 2 rads per second squared. So, for the first one, we have the angular velocity. Now, final angular velocity is going to be, okay, for the first one, we have the angular acceleration. Now, final angular velocity is equal to initial velocity plus angular acceleration times time. Therefore, after 4 seconds, we have is equal to 0 plus 2 times 4, which is 8 rads per second. That is for the first one. We have the kinetic energy gain after 20 revolutions. We can try to calculate the final velocity after 20 revolutions. 1. Or we equate the work done by the torque to the final kinetic energy. Let's look at the two ways. Work done after 20 revolutions is equal to kinetic energy gain after 20 revolutions. And you know that work done by torque will be equal to T theta. T in this instance is 200 Newton meter. Theta here is 20 times 2 pi, which is 40 pi. Please note, 1 revolution is equal to 2 pi. Therefore, work done equals kinetic energy will be equal to 200 times 40 pi, and that is 25,133 joules. That is one way of looking at it. Another way to look at it is this. We know that omega final square will be equal to initial omega square plus 2 alpha theta. What's our initial omega? 0. Alpha is equal to 2 rad per second square. And theta is equal to 20 times 2 pi, which is 40 pi. So, our final angular velocity is equal to 0 plus 2 times 2 times 40 pi, which is 160 pi. That's our final velocity. And you know that kinetic energy is equal to half I omega times 100 times 160 pi. And this is going to be 8,000 pi, which is the same thing as 25133 joules. So you can see the alternative way of going about it. A flywheel has a kinetic energy 200 joules. Calculate the number of revolutions it makes before coming to rest if a constant opposing couple of 5 Newton meters is applied to the flywheel. If the moment of inertia of the flywheel about its center is 4 kilogram meter squared, how long does it take to come to rest? Now, we have a situation like this. We know that the kinetic energy is equal to 200 joules. And we are told that the torque is equal to 5 Newton meter. That is opposing it. Therefore, this kinetic energy must be brought to 0. Must be brought to 0 by this torque. And we have this, that is this, the work done against the kinetic energy should also be equal to 200 joules. Therefore, we can say that 2 kp, let's say kp is equal to T theta. Where theta is the angle revolved in rads. Therefore, you can say 200 joules is equal to 5 theta. Therefore, theta will be equal to 200 divided by 5, which is 40 rads. Now, we have 40 rads. We are asked, how many revolutions is it going to make how many revolutions? So which means that how many revolutions will this 40 rad be? You know that one revolution is equal to 2 pi rad. That is 360 degrees. Remember. Therefore, number of revolutions before coming to rest will be equal to 40 divided by 2 pi, and that is 6.366 revolutions. That is the number of revolutions it makes before coming to rest. We are now told if the moment of inertia of the flywheel about its center is 4 kg/m², how long does it take to come to rest? So we know this relationship that T, torque, is equal to moment of inertia times angular acceleration. Here I is moment of inertia and alpha is angular acceleration. So, and you know what our torque is? T, that is T equals to 5 Newton meter. I equals to 4 kg/m². So we can now see our alpha, angular acceleration, is equal to torque over moment of inertia, which is 5 divided by 4. That is 1.25 rad per second squared. That is our angular acceleration. Now, we know the what's it called? The kinetic energy before the torque is applied. Therefore, we can get our angular velocity at this point. So, angular velocity omega when torque is applied is equal to W naught. Let's make it like that. That is our initial angular velocity. Initial angular velocity. Now let's find what our angular velocity is. Therefore, Ke is equal to half moment of inertia times omega squared. You can now see 200 is equal to half times, we know our I to be 4, and then so initial. Therefore, we can now say omega squared is equal to 100. So omega is equal to 10 rad per second. Now, that's our initial angular velocity. Our final angular velocity is equal to 0 because it came to rest. You understand? Because it came to rest. So it is equal to 0. Therefore, we can now say W is equal to plus alpha t. That is the time. That is the time to come to rest. You get the relationship now. And you can see from here, since it is working against it, it's applied against it. This alpha is negative. So alpha is equal to minus 1.25 rad per second squared. Now, we can now substitute all these values in this equation. That is, omega final is initial plus alpha t. What's our omega final? 0. Our initial is 10. Our alpha is minus 1.25. 1.25 t. So t is equal to 10 divided by 1.25, and that is 8 seconds. A constant torque of 500 Newton meter turns a wheel which has the moment of inertia 20 kg/m² about its center. Find the angular velocity gained in 2 seconds and the kinetic energy gained. So we have this information. Torque is equal to 500 Newton meter, and the moment of inertia is equal to 20 kg/m². So from here we know what the acceleration is. Angular acceleration and torque is equal to I alpha. Therefore, alpha is equal to 500 over 20, which is 25 rad per second squared. Initial angular velocity is is 0. Okay, no. Let the initial angular velocity and we know that final velocity is equal to initial velocity plus angular acceleration times time. From here, the angular velocity gain is equal to final velocity minus initial velocity, which is alpha t. Therefore, we know that our t is equal to 2 seconds. Therefore, angular velocity gain is equal to 25 times 2, which is 50 rads per second. Assuming it starts from rest, will be equal to half I omega final squared. So that is, let us just assume that this one is 0. So our final angular velocity will be equal to 50 rads per second. So Ke gain will be equal to half times 20 times 50 squared, which is 25,000 joules. That's 25,000 joules. The bullet answer: speed 2.4 revolutions per second with our arms outstretched. When the moment of inertia about the axis of rotation is I, with our hands folded, the moment of inertia about the same axis becomes 0.6 I. Calculate the new rate of spin. So we are told that initial moment of inertia is I. Final moment of inertia is 0.6 I. Initial rate of spin is equal to 2.4 revolution per second, and that will be 2.4. And okay, initial angular speed is equal to 2.4 times 2 pi per second. So we are now asked for the final rate of spin. So final rate, okay, so final rate of spin is equal to n. Therefore, final angular speed is equal to 2 pi n. So this one is rad per second. Is rad per second. Revolution per second. Rad per second. Then we now bring in the use of a formula that is omega initial times I initial is equal to omega final times I final. And from the question, we are also given I final is 0.6 I. So let's now put it. So we can now say initial I times 2.4 times 2 pi is equal to I final, that is 0.6 I times 2 pi n. So we can cut this, cut this, cut this. Therefore, we realize that n equals to 4 revolutions per second. So the final revolution, the new rate of spin is 4 revolutions per second, or 8 pi rads per second, or 4 times 2 pi rads per second, which is 8 pi rads per second. So that is it. A disc rolling along a horizontal plane has a moment of inertia 2.5 kg meter squared about the center and a mass 5 kg. The velocity along the plane is 2 meters per second. If the radius of the disc is 1 meter, find the angular velocity. 2. The total energy, rotational and translational of the disc. Rotational and translational of the disc. So we have a situation like this. and we have a radius of 1 meter, and it is moving, rolling along this place. And we are told that it has a velocity of 2 meters per second. Mass 5 kilograms. So, and we are told that it has I, moment of inertia, 2.5 kilogram meter squared. So, we ask the angular velocity. Very simple and straightforward. Angular velocity will be equal to V over R, which is 2 over 1, and that is 2 rad per second, because it's rolling, it's giving us that motion. So the rolling gives us the 2 meters per second, hence it rolls by 2 rads per second. We are now at the total energy, rotational and translational. Because it is rotating, rotational energy K is equal to half I omega squared. Translational, because it is also moving straight, not just that it is stationary and it's rolling, it is moving. So we have translational. This one is translational, this is the rotational. Translational energy, that is kinetic, will be equal to half mv squared. So here we have half, what is I? 2.5. What is omega? 2 squared. This one is half times 5 times 2 all squared. So the total will be equal to half, because we have this in common, times 7.5 times 2 squared. So this one will give me 2. So I have 15 joules. That one gives me 15 joules. A wheel of moment of inertia, 20 kilogram meter squared, about its axis is rotated from rest about its center by a constant torque T. A wheel of moment of inertia, 20 kilogram meter squared, about its axis is rotated from rest about its center by a constant torque T, and the energy gained in 10 seconds is 360 joules. Calculate 1, the angular velocity at the end of 10 seconds. 2, T. 3, the number of revolutions made by the wheel before coming to rest if T is removed at 10 seconds, and the constant opposing torque of 4 Nm is then applied to the wheel. Now, we have a wheel like this, and we are told that it has moment of inertia, wheel of moment of inertia 20 about its axis is rotated from rest about its center by constant torque T. So we have T, torque. Okay, let me start. So our moment of inertia I is equal to 20 kilogram meter squared. Mass about its axis, and we are told that C is unknown. After 10 times T, 10 seconds, energy gained is equal to 360 joules. And the initial velocity is 0. Calculate 1, the angular velocity at the end of 10 seconds. 2, T. Now let's see how we can go about this. We know that our kinetic energy is 360 after 10 seconds, and it's equal to half I omega squared. Therefore, and we know what our I is 20, which is half times 20 omega squared. Therefore, omega squared is equal to 360 divided by 10, which is 36. Omega after 10 seconds is equal to 6. That is root of 36. We have known that. And we are not asked, what is T? T. We know that. Now, we know that T equals I alpha. And what is our I? So 20 alpha. This is the second part. And we know one thing, that after 10 seconds, we have 6 rads per second. Initial is equal to 0. Final is equal to 6. Therefore, and time is equal to 10. So we can find our alpha here. We can now say WF is equal to omega 0 plus alpha t. What is this one? 6. What is this one? 0. What is this one? Unknown, but you know time. So alpha is equal to 6 over 10, which is 0.6 rads per second square. So we have gotten that. So from this now we can find our t. Therefore t is equal to 20 times 0.6, which is 12 Newton meter. We have gotten our t now. We are now asked the number of revolutions made by the wheel before coming to rest. 50 is removed. Okay, now we have a new t. T2 is equal to 4 Newton meter. And the kinetic energy at that time, Ke now, is equal to 360 joules. And we know that T theta is equal to work done. And the work done to bring it to rest. The work done to bring it to rest must be equal to the kinetic energy. Work done to bring it to rest is equal to kinetic energy. From law of conservation of energy. So we are now asked the number of revolutions made. We can now find the angle described, the angle that it moves through before coming to rest. Let's find that. So we can say 4 theta is equal to 360 joules. So theta is equal to 360 over 4, which is 90 rads. So we have 90 rads. It moves through 90 rads before coming to rest. And we know that 2 pi rads is equal to 1 revolution. Therefore, 90 rads will be equal to 90 over 2 pi revolution, which will be equal to 14.324. 14.324 revolutions. So that is the number of revolutions it will describe before coming to rest. A uniform rod of length 3 meters is suspended at one end so that it can move about an axis perpendicular to its length. The moment of inertia about the end is 6 kg/meter square, and the mass of the rod is 2 kg. If the rod is initially horizontal and then released, find the angular velocity of the rod when 1. It is inclined at 30 degrees to the horizontal, 2. Reaches the vertical. Now we have a situation like this. We are told that it is initially like this, and also we are told it is uniform. That is G, center of gravity, will be at the middle here. So the whole mass will be taken to pass through the center of gravity. And we are told that the mass is 2 kg. And we are also told that I is 6 kg/meter square. The length is 3 meters. The length is 3 meters. And then we are told that it is now released to move. Initially, we are asked to find the angular velocity when t is 30 degrees and when it is horizontal. That is when it is 90 degrees. So now the potential energy from here to here, that is converted from here to here, you can get that one. And what will that be? Because we can see that the mass is concentrated at the center of gravity. So you can now take this place as 1.5 meters. So let's take this as our h. So PE, potential energy from this place to this place, we can get it. And that will be, let's call this one x. Okay, let's call it L. L. So H will be 1.5 sine theta. That is the H. And the PE, potential energy, will be equal to mgh, which is 2 times 10 times 1.5 sine theta. Because H varies directly with the sine of the angle. Now, when it gets to this point, it's as smooth, translational, and rotational. Therefore, total energy at angle theta will be equal to rotational plus translational. So rotational and translational. What is the rotational energy? It is half I omega squared plus half m v squared plus half m v squared. That is what we have. I omega squared plus half m. V is L omega. So L omega squared. Therefore, we are going to have half I plus ml squared into omega squared. So you can see. So which means that the potential energy will be converted to the rotational and translational energy here. So when it's inclined at 30 degrees, we can find our potential energy that is expended. When it reaches the vertical, that is 90 degrees, we can calculate our potential energy that is expended. Then we equate it to this equation. Therefore, when inclined at any angle, we can find our angular velocity, that is PE equals to kinetic energy plus rotational energy. Therefore, we can say 2, or let me say mgh is equal to half I plus ml squared into omega squared. So omega squared is equal to mg L sin theta, mg L sin theta divided by half I plus ml squared. So when theta is equal to 30, so when theta equals to 30 degrees, we are going to have omega squared to be equal to 2 times 10 times 1.5 times 30 divided by half into 6 plus 10.5 4.5, that is 2 times 2.25. So omega squared will be equal to, let me call this, okay, this one will be 15 divided by half into 10.5, which is 30 over 10.5. Omega will be equal to square root of 30 over 10.5. And that will be equal to 1.69 rad per second. 1.69 rad per second. Approximately 1.7 rad per second. Now, we also asked when it reaches the vertical. And when it reaches the vertical, that means our theta has become 90 degrees. That means our theta has become 90 degrees. So sin theta. So we can now say, let's just change this. So when theta is 90 degrees, that is, reaches vertical, I'll show you that. When it gets to this place, I drew it. So that's 90 degrees. So this one will be sin 90. So that is going to give us, let's see. So what does that give us? This one is 30 already. So omega squared is equal to 30 divided by half into, this one does not change, 10.5, which is equal to 60 over 10.5. So our omega will be equal to square root of 60 over 10.5. And that will be so that is approximately 2.39 rad per second. We have 2.4 rad second. So that is how this one goes. A recording disc rotates steadily at 45 revolutions per minute on a table. When a small mass of 0.02 kg is dropped gently on the disc at a distance 0.04 meters from its axis and sticks to the disc, the rate of revolution falls to 36 revolutions per minute. Calculate the moment of inertia of the disc about its center. So here, we are going to use the principle of conservation of angular momentum. Principle of conservation of angular momentum. Let's extract our data. Our initial rate of rotation. Initial rate of rotation is equal to 45 revolutions per minute. 45 revolutions per minute. And we can convert this to, so this will be equal to, so that is angular velocity will be equal to 45 times 2 pi over 60 rad per second. Initial moment of inertia. Let's call that one I. So final rate of rotation. So we are told is 36 revolutions per minute. Therefore, final angular velocity will be equal to 36 times 2 pi over 60 rad per second. Then, our final moment of inertia is equal to I plus mr squared. And what is our m? 0.02 kilogram. What is our r? Times 0.04 squared. That is our final moment of inertia. And from conservation of angular momentum, we can say I initial plus times omega initial is equal to I final times omega final. Therefore, we can now say I times 45 times 2 pi over 60 is equal to I final I plus 0.02 times 0.04 squared times 36 times 2 pi over 60. So let's cut this. So if I cut both sides by 9, so this one will give me 4 and this one will give me 5. Therefore, I can now say 5i equals to 4i plus 4 times 0.02 into 0.04 squared. So subtracting 4i from both sides, I have I to be equal to 4 times 0.02 times 0.04 squared. And that will give me that is 1.28 times 10 to the power minus 4 kilogram meter squared. That is the initial, that is the moment of inertia of the disc. A disc of moment of inertia 0.1 kilogram meter squared about the center and radius 0.2 meter is released from rest on a plane inclined at 30 degrees to the horizontal. Calculate the angular velocity after it has rolled 2 meters down the plane if its mass is 5 kilograms. Now we have a situation like this, just like what we did in the example. And the angle here is 30 degrees. The distance here, we are told is 2 meters. And we are asked to find, it rolled down to this place. And we are asked to find omega here. The potential energy here is equal to mgh. And what is our h? H is equal to 2 sine 30 degrees. What is our m? 5. What is our g? Let's take as 10 meters per second squared. At this point, all this kinetic potential energy, all the potential energy is converted to rotational and translational energy. So here, our rotational energy is equal to half I omega squared. Our kinetic energy is equal to half mv squared. And you know that will also be equal to half m r squared omega squared. So you can see what we have now. So PE at the height will be equal to rotational energy plus kinetic energy at the base. So we have NGH is equal to half I omega squared plus half m r squared omega squared. And by the way, we are told what our r is. Our r radius is 0.2 meters. So let's quickly see what our omega will be. So we now can say this one is equal to half omega squared into I plus mr squared. So omega squared is equal to 2 mgh over I plus mr squared. Straight and direct. And we know our h is 2 sin theta. That is, if we make these two to be s, so it's going to be 2 times, what is our n? 5 times 10. What's our h? 2 sin 30 divided by, what's our I? Our I is 0.1 kilogram meter squared. So this one is 0.1 plus 5 times the radius, 0.2 squared. So by the time you look at this one cancels out because this one is 0.5. So this is 1500 divided by, let's see, 0.2 squared times 5. So divided by 0.3. So omega is equal to square root of 1000 over 3. And that will be 18.26 rad per second. A flywheel rotates about a horizontal axis, fitted into friction-free bearings. A light string, one end of which is looped over a pin on the axle, is wrapped 10 times around the axle, and that's mass 1.5 kilograms attached to its free end. If the moment of inertia of the wheel and axle is 0.1 kilogram meter squared, and the diameter of the axle is 5 centimeters, calculate the angular velocity of the flywheel at the instant when the string detaches itself from the axle after 10 revolutions. So we have a situation like this. We have a flywheel and then attached to an axle which is attached to a frictionless pulley like this. And now we have string attached to a pin revolved 10 times, and this one is now attached like with a mass of 1.5 kg. So which means that this will move with the length of the cord down and convert that energy to the translational energy of the mass, kinetic energy of the mass, and rotational kinetic energy of the flywheel. So what do we have now? The moment of inertia of the flywheel and axle is 0.1 kilogram meter squared. Yes, I've gotten the mass here. And now the distance moved before the mass is detached from this combination. Let us get that one. That is the length of the string. Length of string is equal to 10, that is number of revolutions. Okay, let me make this. Number of revolutions times circumference times pi d, circumference of the axle. And that is going to be 10 times pi times 5 over 100. Remember, the diameter of the pipe is 5 centimeters. Please note. So we are going to have this one called this 0.5 pi. That is the length of the string. So the potential energy that will be transferred to the string and the mass, PE gained before the detachment of the mass, before mass detaches, is equal to mgh, and that is 1.5 times 10, that is acceleration due to gravity, times h, 0.5 pi, times h, 0.5 pi. So this will be 1.5 times 5 pi. So that's going to be like 7.5 pi. I think that one is better like that. 7.5 pi. Now, let's now calculate the rotational kinetic energy of flywheel, and that is half moment of inertia times angular velocity, and that will be half times 0.1 omega squared. Now, translational kinetic energy of the mass before it falls off is going to be half mv squared, and we know our v is the radius of this times angular velocity, and I'm going to have half, what's the mass? 1.5. What is the radius? 2.5 times 100. 2.5 divided by 100. The radius is 2.5 divided by 100 times omega, all squared. So this one is squared too. So everything here is squared. Therefore, the potential energy PE is equal to rotational kinetic energy of the flywheel plus translational kinetic energy of the mass. Therefore, I can say 7.5 pi will be equal to half omega squared into 0.1 plus 1.5 into 0.025 all squared. Therefore, omega squared will be equal to 2 times 7.5 pi divided by 0.1 plus 1.5 times 0.025 squared. So let's find, so our omega, straight so that I don't waste time, will be equal to square root of 15 pi, okay, 15 pi divided by 0.1 plus 1.5 times 0.025 squared. So let's see what the answer will be like. So this is the answer of omega squared, and this is the square root, 21.61 rad per second. So that is the angular velocity. That's the angular velocity. A uniform cylinder, 20 centimeters long, suspended by a steel wire attached to its midpoint, so that its long axis is horizontal, is found to oscillate with a period of 2 seconds when the wire is twisted and released. When a small disc of mass 10 grams is attached to each end, the period is found to be 2.3 seconds. 2.3 seconds. Calculate the moment of inertia of the cylinder about the axis of oscillation. So we have a situation like this. The cylinder is like this, and the wire is fixed at this point. When the wire is twisted, it is released. We are told that let's call the moment of inertia to be I. Moment of inertia of cylinder is equal to I, kg meter squared. So when it is twisted and released, we are told that the revolution is the period is 2 seconds. That is, for it to twist once round is 2 seconds. So we can now say omega is equal to 2 pi over 2. That is okay. But mind you, it is the energy that is being converted, the torsion energy that is being converted. We are now told that of the wire, mass of 10 grams is attached here and here. So this has automatically increased the moment of inertia. And now, let us write the angular velocity in this instance. We are told that the period is 2.3. So it's going to be 2 pi over 2.3. Please note, omega, that is the angular velocity, is always 2 pi over period. So which is most times represented as 2 pi over c. Here c is the period. So take it like that. So this is the first one. Now, the moment of inertia has increased in this instance. From here to here is 10 cm. And from here to here is 10 cm. So our new moment is equal to initial I plus mr squared, summation mr squared. Summation mr squared. And that's going to be I plus, what is our m? Is 10 over 1000 convert to kilogram times 10 over 100 squared. That is for this one. For this one too, we are going to have 10 over 1000 times 10 over 100 or squared. So that is our new I. And that's going to be I plus 2 times 10 over 1000 times 100 over 10,000. So take notes. Let's now cut. So I'm going to have I plus 2 over 10,000. So that's our new I now. Our division of energy. It is the energy in this place that is initially applied and gave us this one for the first one. Again, so that energy is transferred. So the energy is equal. Therefore, for the first one, we have I, half I, omega 1 squared is equal to half I2 omega 2 squared. Now, I can cancel this. Let me cancel this. I cancel half. So what is my initial I? Still looking for it. My first omega is 2 pi over 2 all squared. Squared is equal to I plus 2 over 10,000 times 2 pi over 2.3 or squared. Can you see? And looking through this, you can decipher that this one will cancel this one because it is 4 pi squared. And now let me multiply with the LCM, that is 2 times 2.3. So I'm going to have 2.3 squared I is equal to 2 squared into I plus 2 squared times 2 over 10,000. So you can see. Now let me just bring this one here. So I'm going to have, subtracting 2 squared I from both sides, I'm going to have I into 2.3 squared minus 2 squared is equal to 8 over 10,000. So I will be equal to 8 times 10 raised to the power minus 4. 8 times 10 raised to the power minus 4 divided by 4.3 times 0.3. And what would that give me? So our I, the I is equal to 6.2 times 10 raised to the power minus 4 kilogram meter squared. That's the answer. A flywheel of moment of inertia 0.32 kilogram meter squared is rotated steadily. Please take note of the word steadily at 120 rads per second by a 50 watt electric motor. 1. Find the kinetic energy and angular momentum of the flywheel. 2. Calculate the value of the frictional couple opposing the rotation. 3. Find the time taken for the wheel to come to rest after the motor has been switched off. Here we have a flywheel. The moment of inertia 0.32 kilogram meter squared. Angular velocity is 120 rads per second. And power of the electric motor maintaining that steady motion is equal to 50 watts. Now we have to find the kinetic energy and angular momentum of the flywheel. So 1. Kinetic energy is equal to half I omega squared, and that is half times 0.32 times 120 squared. And that's easy. and that is 2,304 joules. Now we have to find the angular momentum as well. Angular momentum is I omega, and that is 0.32 times 120, and that is 38.4 kilogram meter squared per second. Kilogram meter squared per second. Now the second portion said calculate the value of the frictional couple opposing the rotation. Now, 2. You know, in linear motion, the calculated power to be equal to force times velocity. Remember. And if you look at this, you can still break it down further to see force times R times omega. If you look at this, Fr is equal to torque. And so power is equal to torque times omega. We have gotten this. Even from power, from work over time, you know, work is T theta. That is the angle. So it's work. So power. We also say power as T theta over time, which is T omega. So that is power. So we have gotten our value for power now. So we can now say 50 is equal to the opposing torque times 120. So T, therefore, opposing frictional force, opposing frictional torque is equal to 50 over 120, and that is equal to 0.4167 Newton meter. We have gotten that. Now the next one says that we should calculate the time taken for the wheel to come to rest after the motor has been off. If you remember, linear momentum and opposing force, you know, the change in momentum divided by the force will give us time. So let us see. So we can see that change in angular momentum divided by change divided by opposing friction for torque will give us time. So we can now say 38.4 divided by 5 over 12, which will be 38.4 times 12 over 5. I guess it. That is 92.16 seconds. So it will require 92.16 seconds for it to come to rest. In the design of a passenger bus, it is proposed to derive the motive power from the energy stored in a flywheel. The flywheel, which has a moment of inertia of 4 times 10 to the power 2 kilogram meter square, is accelerated to its maximum rate of rotation, that is 3 times 10 to the power 3 revolutions per minute, by electric motors at stations along the bus routes. Calculate the maximum kinetic energy which can be stored in the flywheel. If at an average speed of 36 km per hour, the power required by the bus is 20 kilowatts, what would be the maximum possible distance between stations on the level? So, we know that the moment of inertia of the flywheel is equal to 4 times 10 to the power 2 kilogram meter square. And we know that the rate of rotation of the flywheel, is equal to 3 times 10 to the power 3 revolution per minute. And that is the maximum, please. Maximum. Let me put it here. Max. So, with this, we have 3 times 10 to the power 3 over 60 times 2 pi rad per second. And if you look at this, 60 in 3000, that's 50 times, that's 100 pi rad per second. Fine. So we have gotten some things now. So we are now asked to calculate maximum kinetic energy that can be stored in the flywheel. So, first one, maximum kinetic energy that can be stored will be equal to half I omega mass, square mass, and that is half times 4 times 10 raised to the power 2 times 100 pi all squared. And let's see what that gives. So it gives me approximately 2 times 10 raised to the power 7 joules. The second one says if at an average rate of 36 kilometers per hour, the power required by the bus is 20 kilowatts. What will be the maximum possible distance between the stations? For it to consume the whole power, it means that it's going to consume 20 kilowatts, 20 kilojoules per second. That's what it consume. So let me explain that. The bus consumes average of 20 kilojoules per second. Therefore, time to consume 2 times 10 raised to the power 7 joules will be equal to 2 times 10 raised to the power 7 divided by 20 times 10 raised to the power 3. So what does that give me now? This one is 10. So it's 10 raised to the power 3 seconds. So which means that the time to travel from one train station, from one bus station to the other is 10 raised to the power 3 seconds. Therefore, the distance, to calculate the distance is equal to speed times time. And we have the speed in kilometers per hour. So for us to work with this, you have to calculate it to, you have to convert it to kilometers per to meters per second, or we can convert this one to hours. So either of the two. So we can say 36 kilometers per hour times 10 divided by times 10 per 3 divided by 3600. So you can do it like this because 3,600 seconds will make 1 hour. So since we are making it per hour, so the number of hours in, this is the number of hours in. So this one will now be 100. So which means that the distance is 10 kilometers. The distance from one station to the other will be 10 kilometers. Or if I say I convert this one to, so it's going to be 36 times 10 over 36. That is meters per second times 10 raised to the power 3. So this one, so this should be 10,000 meters, and which is 10 meters. So either way, you get the same answer. The atoms in the oxygen molecule O2 may be considered to be point masses separated by a distance of 1.2 times 10 raised to the power minus 10 meter. The molecular speed of an oxygen molecule at STP, standard temperature and pressure, is 460 meters per second. Given that the rotational kinetic energy of the molecule is 2/3 of its translational kinetic energy, calculate its angular velocity at STP, standard temperature and pressure, assuming the molecular rotation takes place about an axis through the center of and perpendicular to the line joining the atoms. So what do we have? We have a situation like this. You know that this is how the molecules are. So there is a line connecting the centers. So we are made to say, okay, look at it from the perspective that it is just like this. So there are, and it is rotating about its center here. So from here to here is 1.2 times 10 raised to the power minus 10. 1.2 times 10 raised to the power minus 10. So it means from here to here, the center will be 0.6, or let me say 6 times 10 raised to the power minus 11 meters. And same here. So we have it like this. And we are made to see it like it is rotating and moving straight, like this. It is rotating and at the same time moving forward. We have a situation like rotational and translational. So let us now work on it. The mass is equal to n. Okay, let's make it n. And the velocity v, translational, is 460 meters per second. Now, the Angular velocity. We don't know that. But we know that the mass of this one, the mass here is m/2 and the mass here is m/2. So we have like this, m/2, m/2. So to calculate the moment of inertia for this, we can now say I will be equal to 2 times m/2 times 6 times 10 raised to the power minus 11 all squared. So that's our I. We're also given another information that, okay, let's find the kinetic energy translational is equal to half m v translational squared, which is half m times 460 squared. Kinetic energy rotational is equal to half I omega squared, which is half times 2 times m/2 into 6 times 10 raised to the power minus 11 all squared omega squared. And we are told that this one is 2/3 of this. This one is 2/3 of this. So we can now say K ER is equal to 2/3 K E. So with this, we are on the way of solving our problem. So we can now say half this one n into 6 times 10 raised to the power minus 11 all squared omega squared is equal to 2/3 times half n 460 squared. So let's cancel this. This one too will be cancelled. Now, and from here, I can now calculate my omega squared. It will be equal to 2/3 times 460 squared over 6 times 10 raised to the power minus 11 all squared. So omega is equal to 460 over 6 times 10 raised to the power minus 11 square root 2/3. Because square root of this will bring this out. So let me solve that straight. So, omega is 460 over 6 times 10 raised to the power minus 11 times root 2/3. So I made it 46 over 6 times 10 raised to the power 12, because this one will be times 10 here. So at the end of the day, I got 6.26 times 10 raised to the power 12 rads per second. And I can still approximate it to 6.3 times 10 raised to the power 12 rads per second. So you can see, very straightforward and easy.